then. Our next and last speaker is Wenlei Zhang of Tulane University. And he's going to talk about violating the Leggett-Garg inequality with classical light. So, welcome, Wenlei.
Thank you, Peter, for the introduction. And since I'm the last presentation, I'm going to keep this nice and short. So first, I want to begin by thanking the organizers for giving me this chance to talk about our work on violating the Leggett-Garg inequalities with classical light. So first, I'm going to introduce a little bit of background information, mainly on the Leggett-Garg inequalities. Then I'm going to introduce the mathematical framework that we use to describe our experiments, the Jones calculus. And then I will show you the experimental setup and our results, and I'll finish with a summary. So first of all, what are the Leggett-Garg inequalities? So everyone knows the Bell's inequalities. So in contrast to Bell's inequalities, which test the correlation between measurement of multiple systems, the Leggett-Garg inequality tests the temporal correlation between measurements of a single system. Now, it is important to understand the assumptions under which the Leggett-Garg inequalities are derived. So the first two assumptions were proposed by Leggett-Garg in their original paper in 1985. So these are direct quotes from their paper. So I'm just going to read them so that we don't have any misunderstandings in translation. So the first assumption is called macroscopic realism, which says that a macroscopic system with two or more macroscopically distinct states available to it will at all times be in one or the other of these states. And the second assumption is called non-invasive measurability, which says it is possible in principle to determine the state of a system with arbitrary small perturbation on subsequent dynamics. Now, the third assumption was added later on by Leggett and others, and it's called induction, which says that the outcome of a measurement on the system cannot be affected by what will or will not be measured on it later. So even though A3 is necessary for the derivation of the Leggett-Garg inequalities, you can see that A3 reflects the notion of causality and arrow of time. So A3 should be satisfied by both classical and quantum systems. But it is obvious that quantum mechanical systems will violate the first two assumptions, and measurements in time on quantum mechanical systems will violate the Leggett-Garg inequalities. And the conjunction of these three properties are sometimes referred to as classicality in literature. But in my personal opinion, that is a little bit confusing. And I think it is better to refer to each assumption explicitly when we're discussing these issues. So in the simplest scenario, the Leggett-Garg inequalities is given by this equation, equation 1, where T1, T2, T3 are points in time, different points in time where the measurement is made, and Q is some dichotomic observable. So there is a fundamental difference between tests of local realism and macro realism. So for macro realism, there is no Fein's theorem. So recall that Fein's theorem for Bell's inequalities says that Bell's inequalities are necessary and sufficient condition for the test of local realism. But the authors here in reference 1, they found that no set of inequalities can ever be necessary and sufficient for a macro-realist description. So Bell's inequalities are related to entanglement. And similarly, the Leggett-Garg inequalities are related to what is called entanglement in time. But there are nuanced differences between these topics. So I highly encourage everyone who is interested to read more on these topics. So here I'm showing a few examples of previous experimental violations of the Leggett-Garg inequalities in optical systems done by other groups. So the first two examples were done with single photons. As you can see from the setup, they have a SPDC crystal. Now, single photons are far from macroscopic objects. So in my opinion, using single photons to test for macroscopic realism is not very satisfying. So because even if single photons, even if a microscopic system violates macroscopic realism, that does not necessarily tell us anything about how macroscopic systems should behave. So, okay, the third example uses not single photons, but classical light. But they use the interplay between the orbital angular momentum and polarization of light, as you can see with their CNOT gate here. And this is like, for lack of a better term, what some people call classical entanglement. So what we want to do in our experiment is we want to demonstrate the violation of the Leggett-Garg inequality in a classical optical system using only the polarization degree freedom of a laser beam. So these three examples are for optical systems, but the Leggett-Garg, violations of the Leggett-Garg inequality has been demonstrated using other systems such as superconducting qubits, nuclear spins, and light matter interactions. So before I show you our experimental setup, I would like to describe how, like, the mathematical framework that we used to describe our experimental setup. So we choose to use the Jones calculus to describe the polarization. There are several different mathematical tools that you can use to describe polarization, but this is the one that we are using. So before I start describing, I want to note that the quantities with the hash symbol denotes matrices within the context of Jones calculus, not quantum mechanical operators. So this description is completely classical. So in the Jones calculus, the state of polarization is described by a 2x2 Hermitian and positive semi-definite matrix rho. The reason that it's a 2x2 matrix is because for a transverse electromagnetic wave, the electric field only has two components. So the diagonal terms of this 2x2 matrix describes the two components, and the off-diagonal terms describe the correlation between components. Physically, the trace of rho is the total intensity of the light that would be detected by some detector. And optical components in the Jones calculus are also described by 2x2 matrices. And here I've written them with letter J. So they are called Jones matrices of some optical component. And the polarization matrix rho is transformed to J times rho times J dagger when the light passes through that optical component. And there are many optical components that we can model in the Jones calculus, but for our experiments, we're only concerned with wave plates and polarizers. So wave plates are unitary matrices in the Jones calculus, and polarizers are described by projection matrices. So here are two examples of, the first example is the horizontal linear polarizer, and the second is the vertical linear polarizer. So here is the experimental setup we use to demonstrate the violation of the Leggett-Garg inequality. So first of all, in Gaussian optics, under the paraxial approximation, the time evolution is equivalent to the propagation along its optical axis. The time evolution of a laser beam is equivalent to the propagation along the optical axis as shown in figure A here. So for simplicity, we choose the time evolution operator, the unitary U matrix here, to be the same in each time step, but in general, they don't have to be. And the U is realized by using two halfway plates as shown in figure B here. And the exact value of the elements of U is determined by the rotation, the angles of rotation theta 1 and theta 2 of the two halfway plates. So figure C to E shows the setups that we use to measure each of the three correlation functions in the left-hand side of the Leggett-Garg inequality. And in all of these setups, the observable being measured is the Pauli matrix sigma 3. And this measurement is done via a polarizing beam splitter. And we map the projective measurements onto the values plus and minus 1, where +1 represents measuring horizontal polarization and -1 represents measuring vertical polarization. And the values of in the parentheses after the intensity just denotes where the measurement result is made. So the first number represents the measurement result at Ti, and the second represents the measurement result at Tj. So to get, for example, to get the setup To get the setup shown in figure C, in figure C, we're trying to measure QT2 and the QT1, the correlation between T2 and T1. So we just place beam splitters at T2 and T1 in figure A to get the setup shown in figure C. So we measured these 12 intensity measurements, and the correlation functions are calculated from these intensity measurements using equation 3 here. And finally, equation 4 is just showing the left-hand side of the Leggett-Garg inequality again, and we denote this value by K3Q. Now, we also want to theoretically calculate what K3Q is. And to do that, we use these equations here within the Jones calculus. So here I'm showing the measurement to measure QT2 times QT1 again as an example. So to calculate each of the intensities, we just applied each optical component to rho in sequence and take the trace of the final polarization matrix. And here the matrix P is just equal to either the horizontal polarizer or the vertical polarizer, depending on the value of M or N. And U is the total Jones matrix of the two halfway plates that I showed in the previous slide. And then after we get all these intensities, we plug it into the equations that I shown before to get the theoretical values of K3Q. So here on the left plot, I'm showing the theoretical calculation of K3Q for various values of theta 1 and theta 2. Now I'm only showing two colors because I'm just showing the part where K3Q is larger than 1 and the part where K3Q is smaller or equal to 1. So blue represents the region where K3Q is smaller or equal to 1, and the red is where K3Q is larger than 1. So K3Q larger than 1 means that the Leggett-Garg inequality is violated there. And so on the right plot, I'm showing that our measured results. And on the top, the initial state is the diagonal polarization state, where diagonal is just the superposition of H and V with a zero phase in between H and V. And the bottom plot on the right shows the initial state for L and R. And so it's important to note that the theoretical values of K3Q does not depend on the initial state. That's why the theory curves in these plots are all exactly the same. And our measured results lie pretty close to the theory curve. So you see in some regions of theta 2, the Leggett-Garg inequality is violated. And our measured results show that also. So here is a plot where we use a mixed initial state. Yeah, the previous two initial states were our pure states. So here we are changing it to a mixed state where when we're talking about polarization, it should be a partially polarized state. So the degree of polarization, which describes the amount of polarized light to the total light, is about 0.8. That corresponds to a trace of rho squared of about 0.8 also, that's coincidentally. And again, the theory is exactly the same as before because the K3Q does not depend on the initial state. And our measured results also lie pretty close to the theoretical values, except for some points. For example, this point is a little bit farther away. And there are some points where we are actually above the theoretical limit, which should not happen. This is probably because of our experimental errors. So the main experimental error is the fluctuation of the laser intensity during measurements. So because we have to take 12 intensity measurements to get one data point, the laser fluctuation will cause this kind of error. And we would like to repeat this experiment for maybe a completely unpolarized light where the DOP is close to 0 and the trace rho square is close to 0.5. But that is hard to do experimentally because to get unpolarized laser beam, you will need to introduce some kind of decoherence somewhere by using either by introducing spatial or temporal coherence. But that is it's hard to introduce decoherence and keep the whole system stable. So we are trying to do that. So to summarize, we experimentally demonstrated the violation of the Leggett-Garg inequality in a classical optical system using only the polarization, and which implies that the classical wave mechanics is not consistent with assumptions A1 and or A2. So upon further consideration of this problem, I think that the reason that the Leggett-Garg inequalities are violated is because of the superposition principle. So the reason, right, so polarization comes from Maxwell's equations, which are completely classical. And the reason that we describe polarization was using the Jones, that we can use the Jones calculus to describe polarization, and the Jones calculus looks so much like the density matrix description of a quantum two-level system, is because we can have two orthogonal polarization state and also any linear combination of those two orthogonal states is still a solution of the Maxwell's equation. So this superposition principle is not exclusive to quantum mechanical systems. And that is all I have for you today. Thank you for your attention, and I'm happy to answer any questions.
Thank you, Wenlei. I have a question of my own. If you go back to those assumptions, one of them was macroscopic realism, I think.
Yes.
So a macroscopic system with two or more macroscopically distinct states. In the experiment you're doing, are the two macroscopically distinct states horizontal and vertical polarization?
Right.
So a
That is
diagonally polarized beam of light is not in
be
one of those two states.
Yeah, that's what I tried to explain at the end there.
Uh-huh.
So their definition of macroscopic realism is similar to the notion of realism conceived by Einstein, Podolsky, and Rosen, where it's kind of similar, right? So where they say that you have more than one state, it has to be in one of those states. And this, right, so it's an argument for macroscopic systems, but not necessarily for, like, they don't have the word classical in there. It's there, so they're not considering whether the system is described by classical mechanics or quantum mechanics or anything like that. But it says two or more macroscopically distinct states. So yeah, in our opinion, the polarization, the vertical and horizontal polarization are two distinct states, but you can have the superposition of those states.
Right, you keep saying superposition, but I'm just thinking about, like, literally, if I wave a slinky up and down, that would be horizontally polarized. If I wave a slinky from left to right, that would be vertically polarized, or vice versa. But then if I swing it in sort of the diagonal direction, are we just, is that just saying that, well, we've disproved that the only things a slinky can do is up and down and left and right?
No, I think what it says is that if you consider the two 45-degree orthogonal, you can only be in one or the other.
Yeah.
Okay.
It's all a question of basis.
Yeah, exactly. So you can also pick left and right, circularly polarized, something like that.
Okay, that seems to have a little more content then. Okay.
You can have more than one pair of bases.
Although it does bother me because it basically says you're already throwing out right at the start that there is no superposition.
Right, exactly. So this assumption, yes, that's right. So the derivation of this inequality relies on this assumption, which means there's no superposition. That's right.
Can I ask a question? This is Mark Weldy. Can you hear me?
Yeah.
Can you go to the slide with the depiction of the experiment that implements the measurements? Yeah, so I was trying to understand this. When I look on the left, I would think, okay, at time T1, I need to do a measurement and collect data about polarization. And then at time T2, I have to do another measurement. And so I was trying to map the picture on the left to, say, like figure C.
Right.
So I didn't quite follow that. So where is the measurement being done at time T1?
So we are using a PBS, but you can just use a regular linear polarizer, right? But the PBS is like two polarizers, but it splits it into two paths. So you can think of just having a horizontal polarizer here, and then another horizontal polarizer here, and then you measure the final intensity. That would just be this intensity here.
Okay, so is it that if it goes in the upper arm, then you know that it's like one polar?
One. So it's measured horizontal and horizontal here. So it's 1, 1. And this intensity tells us the intensity that we measure horizontal both times.
Okay, but the thing is, the way that you're doing the measurements, you're not getting discrete outcomes, right? Like,
right. Right.
you're allowing for superposition to happen. And so,
well,
like in the first beam splitter, you can have the original state can be a superposition, right? And it can go through the upper arm or the bottom arm, is where, I mean, my impression of Leggett-Garg is that you really have to do a measurement that projects the state.
Right.
Right?
So so I've not shown one example here. We are doing something similar to what other groups have done before, is where they use single photons, but they use coincidence counting here.
Okay.
They count the number of photons, and then they say that that is the correlation function. So the intensity is the number of photons, right?
Mm-hmm.
And the measurement is on the polarization, which is either horizontal or vertical. It is a dichotomic measurement. It's either +1 or -1, the measurement result on each photon. So if we are, again, maybe going back to photons, it's easier to understand. It's the measurement on each photon is dichotomic.
So you're saying that figure C is a simulation of what you could do if
Your
you actually
photon number is bigger, like it's really big.
Say that last part again.
If you have a really large number of photons.
Mm-hmm.
But in this, right, technically it's not exactly that, but here we're using a classical laser beam. But in other experiments done by other groups, the way they generate single photons, one of the ways is to just have a laser beam, and then they attenuate the laser beam by a lot to reach single photon levels. And then they have a single photon counter here. So, right, it's almost the same thing, just by like increasing the number of photons.
So Mark, Dennis, if I may add, so it's basically what Wenlei is saying is that we saw a paper of this year, published earlier this year, that actually was doing Leggett-Garg for single photon states. But Wenlei actually realized that actually the same result will be obtained if we just use a classical light as input, not the single photon state, and that's what he demonstrated.
Mm-hmm. Okay. The other comments I had, if you go forward a few slides, you were showing the data and some of the points were above the, yeah, that one.
Oh.
Go back, that one. Yeah. So there's this kind of persistent problem with the Leggett-Garg inequality. My co-author and I wrote a paper, we called it the clumsiness loophole, where like a skeptical macro realist could attribute the violation that you're exhibiting just to being like a clumsy experimentalist. And so I guess it's maybe presumptuous theorists writing papers with that kind of title. But the fact that you have this experimental data point that's off of the chart of what's even possible could allow such a skeptical macro realist to continue being skeptical.
I see what you're saying, and I've seen that paper. Yes.
Okay.
It is due to, so our setup is a little bit complicated because we have, we don't actually have three setups that look like exactly like this. We're changing the setup. Like we first use setup C to measure the 4 intensities, and then we have to switch over to setup D again, right? And then measure these 4, and then change over to E, and then measure these 4. So in between these switching, the laser is fluctuating a lot, and right, so we're not actually measuring all 12 intensities at the same time, and that is the clumsiness in the experiment. Mm-hmm. Yeah, I agree. That's a big loophole that is hard for us to close. Yeah.
Yeah, that was the key difference between Leggett-Garg and Bell tests. You know, that
Mhm.
as long as you're satisfying the locality assumption, you know, for the Bell test, then you can't have this kind of loophole.
Yeah, right. So yeah,
Yeah,
that is a good point. That is a pretty big loophole. So, well, I'm open to any suggestions on how to improve the experimental setup. But this is the simple experimental setup that we came up with.
yeah. So it was like a decade ago, I was on a Leggett-Garg binge, and we wrote another paper where we showed that there were systems where you, if I remember the result correctly, you couldn't violate the Leggett-Garg inequality, but then there would be experiments with more measurements that could be conducted where you could violate those. So these higher experiments could detect correlations that the Leggett-Garg could not. So I don't know, there might be something of interest. But it was interesting for me to learn about this no find theorem. That seems to kind of,
Yeah, I think that was discussed in this paper.
yeah, that seems
Yeah, because
to
the title is
limit.
called Limitations of the Leggett-Garg inequality. Yeah.
That's right.
Yeah, this is an interesting result. I did not know this before like doing this project.
Mhm.
But do you want to quickly comment on the recent papers on arXiv, like actually about classical physics
Yes.
violating?
There was a recent paper on arXiv by another group where the title is exactly this, exactly my title.
Really? Wow.
Yeah. So in their setup, they are doing a different thing using classical light, where their dichotomic observable is not polarization, but the path. So their unitary time evolution is just a regular 50-50 beam splitter, and then they're looking at which path the classical light takes, where either it's transmitted or reflected. So it's similar to a random walk experiment, I guess. And in that setup, they also claim that you can violate the Leggett-Garg inequality, but their paper is completely theory. They don't have any experimental results yet. So that is another way to do this type of experimental violation using classical light.
I actually had another question. Regarding the assumptions of Leggett-Garg, can you go back to the slide where yeah, that was a nice slide. So regarding A1, is the assumption that there's like a discreteness, there's a finite number of states the system can occupy?
They do not. So in the original paper from 1985, I don't think there's any discussion on that.
Okay, I guess I always thought that was part of it. And then when you go to polarization, there can be, you know, there's a continuum, right?
Right. I mean, it's a whole sphere, the Poincare sphere
Yeah.
picture. You can have states on any point on the sphere.
So like, if you're using polarization, aren't you already outside of the model to which Leggett-Garg applies?
That was kind of my
Yeah, it's related. So I think yes, that's the whole point, is that macroscopic objects do not satisfy this realism definition, right? That's the whole point.
Okay, but then to sort of make a more provocative statement, didn't we already know that before doing the experiment?
Kind of, because these experiments show violation, right? So it depends on how you interpret like single photons versus classical light. Is that like, so people have done measuring the polarization of single photons, and then they show violation of the Leggett-Garg inequality. But then it's up to you. Like, are you satisfied with the results of measuring polarization on just single photons to show macroscopic realism, to test macroscopic realism? Right. It's how right. Yeah, because a single photon cannot be described classically.
Yeah. So Mark, so just once again, I'll repeat this comment that basically how this setup was developed is that Wenlei actually saw a paper, a quantum paper with single photon states, right? And then he realized that actually the same result will be obtained if you just shine a classical light.
I see. So this part of it is to like cast doubt or shade or whatever on this previous experiment.
Not necessarily. I mean, it's not a bad experiment.
I don't see it that way.
No, exactly. So it's not. I would not put it this way. Yeah, but go ahead.
Okay.
Yeah, I would say that the idea of using the classical light is that from the photon angle, you have a very large, it's a macroscopic state because you have a large number of them. So now you're showing that even for that, it violates the inequality.
Yes, that is the idea. That's correct.
And to add this, there's a beautiful picture, right? Analogy, optical analogy between mathematical one-to-one correspondence between description of classical polarization states, which is given by a Poincare sphere, and state of a qubit, which is given by a Bloch sphere. So it's up to just relabeling axes. These are the same things, right? And John's calculus, as Wenlei had on the next slide, is literally like almost axioms of quantum mechanics, right? So it's a beautiful analogy, right? Even though we're dealing with a tremendously large number of photons here.
Yeah, but this comes from like Maxwell's equations, and it's classical.
Yeah.
Okay. Any more questions?
It's a nice experiment.
Thank you.
Yeah, I'm coming around to it now as a sort of response to an earlier experiment illustrating sort of gives it an interesting context, them buying into more as you all explain it to me. Okay, yeah, so thank you, Wenlei, for this last talk. And